Hi and welcome to another edition of Ordinary Differential Equations. Today we are going to talk about forced mechanical vibrations. This is probably the high point of the course, and let's go see what we have ahead of us. So, forced vibrations, we said this refers to a system that can oscillate by itself, but we have an external force that is going to drive the system. So previously we had seen equations where you have my double prime plus cy prime plus ky equal to 0. So 0 on the right hand side meant there is no other force other than what is reflected here, which is force of drag, force of a spring, and perhaps a constant force of gravity. What we are going to do now is next level up, we have an external force. And this is going to make the problem a lot more interesting. Remember the ingredients in this situation. This was our mass. This was the damping coefficient. This was the spring constant. F here stands for the amplitude of the external force. This omega stands for the frequency of external force. The problem is very interesting because it's a standard topic in the theory of vibrations. We said this course can be renamed as the theory of vibration, and this is the high point of that. What will happen in this case? Well, mathematically speaking, this is quite straightforward. We have already done that. Without this force on the right hand side, that was the homogeneous equation. We have learned how to solve that, the three cases and the story that came there. With the right hand side, we looked at the issue already before. We know how to handle that question and actually more extensive cases. In practice, however, putting all of these things together makes the problem become a bit lengthy. So here's a fair warning. We're going to take the kid glove off and dig into this thing a bit more than usual. Here's an example problem, which is probably problem 5 or 6 in your textbook. And let me explain what the problem is, and then we go set out to solve it. And in the process, perhaps the most interesting aspect of this is the issue of resonance, which we talked about in several contexts before. The resonance we are going to talk about today is different from the one that we had previously. Previously, the resonance occurred because the solution of the homogeneous equation had a term in common with the applied force. That brought us an extra factor of t and so on. In this case, we don't have that kind of resonance. What we are going to be looking for is what kind of external frequency is going to lead to highest response from the system. So that's actually more practical and perhaps more important than the resonance we had talked about before. Pretty much all engineering texts do cover this thing, and it's a section that is laden with quite a bit of formulas, lengthy derivations, and so on. But it's all doable, and let's see if we can do it today. So here's a problem. We have a mass of 5 kilogram that when you attach it to a spring is going to stretch it by 10 centimeter. Then the mass is acted on by an external force of 10 cosine of 2t in newtons and moves in a medium that imparts a force of 2n when the speed of mass is 4 centimeter per second. This is talking about the resistance of the medium to movement. So this is talking about the drag force. The mass is set in motion from its equilibrium position with an initial velocity of 3 centimeters per second. Now a long list of things to be done. Formulate the initial value problem. Find the position, graph it, identify transient and steady state parts of the solution, find the amplitude of the steady state solution, and here comes the high point of the problem. If the external force is replaced with 10 cosine of omega t, so originally it was 10 cosine of 2t, now we are making this frequency a variable. Instead of 2, putting some arbitrary omega here. Find the value of omega for which the amplitude of the steady state or forced response is maximum. Okay, this type of problem tend to be lengthy, so again, be ready for that. Many of your homework problems might stop at one place or another in this context, as opposed to asking for all of these inside one problem. Many of them just stop at this level. Formulate the initial value problem, which means the modeling, the phase 1 of the modeling, just convert the statement above to a mathematical equation. Next level up is, of course, to find the solution of that. Next level up is find out some details about that solution. A huge peak, so to speak, for this problem is to do the resonance problem, finding the optimal frequency. So before we dive into this problem one more time, let me remind you, as a high point of this course, in some sense you are instinctively familiar with this issue. Instinctively meaning, for example, if a car is stuck in sand or some ditch or something, and then you're trying to push it out, of course you're not Incredible Hulk. You cannot pick the car out of the ditch and just put it outside. Rather, you have a few friends to go out and push the car, and they rock the car back and forth until you come to the edge of the ditch and you come out. So the critical aspect of that whole operation is at what frequency do you rock the car. If you pick a random frequency, it's not going to work. So what you do, you essentially arrange a dance between yourself and the car. You push it a little bit, it comes back, and then at the right moment you push it again and it comes back higher amplitude, and you repeat that process over and over again until the rocking motion picks up enough amplitude until you can actually push it out of the ditch. So what we are doing now is a mathematical version of that. This is a system very similar to that car being stuck in the sand, and it has you're dealing with a mass, you're dealing with some sort of drag, friction in the system, and it acts like a spring that's swinging back and forth. What is at your disposal in all of these things is the frequency at which you apply the force. And finding the optimal frequency is what does the trick. Another way to explain this thing, if you have, for example, a shelf of books, as you see in the library. These shelves are quite heavy and you cannot move them. But if you start to press against it, the shelf will start to sway back and forth. If you find just the right frequency, then the amplitude of the oscillation of the shelf is going to increase. Of course, you don't want to do it too much because the shelf is going to crash and could cause quite a bit of damage. The interesting aspect is that small amount of force applied for a long time at the right frequency can make an object that is quite heavy to oscillate for it. And that's the interesting part of this, which is referred to as resonance. Okay, now let's go ahead and take this problem. First easy part is translating the problem into a mathematical statement. So what do we need to do? Of course, we need to find these ingredients. In addition, there is an initial condition, y0, y prime 0, and so on. So let's see one at a time. What does this refer to? That's the easiest part. That just refers to m being 5, and then we have to pay attention to the units, kilogram. It stretches a spring by 10 centimeters. Well, we look at this problem, we have to make a decision. If we want to do everything in terms of centimeters and grams, or kilograms and meter, we have to stay consistent so that our solutions are understood by others. So one option is to say, okay, let's convert to meters. In that case, you take this thing divided by 100, and that's going to be in meters now. That's the first stretch. What kind of a clue do you get out of that? The clue you get, of course, is the spring constant. What is the formula there? The formula is the force of the spring is equal to spring constant times the stretch length. Okay, what is the force of spring itself? Well, that's a force that is being imposed by putting this huge weight on it. Well, what is the weight? Well, that requires another formula. That is the formula W is equal to mg. That's the weight of the object. And if the mass is given at 5 and g is in this system is 9.8 meters per second squared, we get our W to be 5 times 9.8. So that's going to be 49. And the name of the units in this system is called newtons. Okay, the system itself is called meters, kilogram, second, MKS system. And inside of that system, G is 9.8 in the units used here, which is meters per second squared. Okay, what do we get out of this? What we get is that the force is this force, which is the weight of the object. That's 49. K we are trying to find, and L is the first stretch, and that is 1/10 of a meter. So this is 1/10. Short end of the story, long story, is K becomes 490. The spring constant is 490. What units you want to attach to it is the unit of force, which is Newton, divided by unit of length, which is meters. So this is newtons per meters. Okay, so far we have our M, that is a crucial aspect. We figured out our K, that is next item. The mass is acted on by external force of 10 cosine of 2t. So that is just telling us that is that. So 10 cosine of, let's mark it, that's our f cosine of omega t. So this is my, this is f cosine of omega t for me. Next, level up. We have to figure out what is the damping coefficient or drag coefficient or whatever is indicative of friction in the system. So it says when this object moves in that medium, a force of 2 newtons is going to prevent the object from moving if the speed of the object is 4 centimeters per second. Let me just remind you again, like the drag force, like when you stick your hand out of the window of a moving car, you feel a force on your hand. Well, the faster that you go, the more force you feel on your hand. Simple way of putting this thing is that the force of drag is some constant multiplied by velocity. The faster you go, the faster the higher the force going to be. This is saying that if you go 4 centimeters per second, the force will be 2 newtons. Well, you have to be careful again. This has to be converted. So this is 4 over 100 meter per second. And well, this force is in the correct units of 2 newtons. So 2 newtons. C velocity is 4 over 100. So obviously C from this turns out to be 50, and the units of that is going to be newtons, seconds per meters. So one more of mystery objects is taken care of. So M, C, K, we know that. F cosine of omega, we know that one too. Okay, what else do we need to set up our problem? We need our initial conditions. Where does it come, initial condition? This is N, this is the mass is set in motion from its equilibrium position. So that is one clue. Let me see, make sure everybody coming along with me. What does that mean? So, 1 second. The mass is set in motion from equilibrium position. What is that? Well, we have to use a letter, so y is already used. So that tells me that when you set it from the equilibrium position, means your initial position is 0. With an initial velocity of 3 centimeters per second. So one more of these things we have to deal with. This is 3/100th meter per second. So what is that? That is y prime 0. Y prime 0, so that's going to be 3/100. Perhaps to make it clear, we have to express set in motion in a downward direction. So to make it clear, let's in a downward direction. Because you can set it in motion either going up or going down. So here we are going to have the following. So the object, let me see. So we have the spring, we attach mass to it, it stretches. Then from this position we kick it downward. So y0 is 0, y prime 0 is 3/100, and we are taking this to be our positive direction. Okay, formulate the initial value problem. So we got all the ingredients. And now it's easy to harvest everything we got. So we had M, we just have, all that means you rewrite this equation for your case. So I have my M became 5, is that right? So 5, Y double prime. And C became 50. 50 Y prime. And K became 490. 490 Y. And the right hand side was just handed to us. 10 cosine of 2t. Together with y0 is 0 and y prime 0 is what we got here, which is 3/100. Okay. One tiny issue is I've been using letter Y most places. Your textbook uses the letter U most places. So allow me to go back and forth to just use the right lettering for whatever the problem refers to. So y or u, same thing. You want to solve this thing, graph it. Okay, before we dive into all that detail, let's get a handle on the problem before we are lost in all the algebra. So we are going to graph this thing. What are we going to see in the graph? There's going to be a transient part and a steady state part. What does that mean? Transient part is a solution of this thing without the right-hand side. So that transient part, because of the exponential factor in it, is going to die off. So what we expect at the beginning, is that perhaps the problem kind of shoots up or something, maybe, and then it settles down to a nice oscillation. So we have a transient to our picture, means a behavior that dies away, and something that stays on forever, and that's the steady state. And this portion is dictated by what you have on the right hand side. You are putting energy into the system from here. The first one, you are giving energy into the system by the initial kick, but that energy is going to die away. It's not going to persist forever. So you see a spike or something at the beginning, or a weird looking graph, and then it just becomes a nice sinusoidal. So that's what this one is referring to. Once you find the solution, transient is what has exponential of negative something times t in it. Okay, so that's the transient part. Steady state is the portion that is just cosine of, well, it's going to be that frequency, cosine of 2t times some number, and then there's going to be some sine of 2t in it as well. That's going to be your steady state contribution. Okay, this is all doable, even though it's going to take a bit of a time to do. The focus for today is this resonance issue. The resonance issue is if I play with the frequency of the right-hand side, if instead of 2 I use some other frequency, what am I going to get out of that? What you get is that the amplitude of this oscillation, the steady state oscillation, is going to go up and down depending on what frequency you're going to have. So at some frequencies, it's going to perhaps look like this. At some other frequencies, you might see an oscillation that is much bigger. And typically in these problems, you either want to be aware of that maximum oscillation, and perhaps you want to stay away from it, or perhaps you actually do want that maximum oscillation, and that's what you are searching for. Let me show you a picture of what we are after, and then we are going to dive into the problem itself and try to do that. So there is going to be a lengthy formula that indicates this graph that you see here, and this is one of the places that Desmos comes in very handy. Let's see. So the formulas that's going to come out, I've already typed up here. I'm not going to read through these things for you, but what I have here, we have a slider for our frequency. Instead of omega, I wrote W here. At this very high frequency, you see that amplitude of oscillation is quite tiny there. Now, as I reduce the frequency, you see that amplitude starts to build up. So right now it's became double, double again. So you're seeing now the amplitude is increasing quite a bit. This is much higher than it was before. At the beginning, you see a weird looking graph. That's where the transient part is. Transient part, you're kicking the system, giving it some energy, but that energy dissipates because of that damping that you have. Now, if I keep playing with this thing, the amplitude of response increases, You see, increased quite a bit. And then it reaches a certain maximum. I've indicated that the maximum by this blue line up here. Now, if I keep playing with the frequency, I lose what I gain. That is, the amplitude comes down. You see, it came below the blue line, and now it came down somewhat. So there is a frequency at which I reach the highest I can be, and if I deviate from that frequency on one end, I lose some percentage, and the other end I lose quite a bit. So here I come here pretty much that amplitude. If I go all the way high, the amplitude drastically falls, and somewhere in the middle in this problem it turns out to be the square root of 48. That's 6.9 or something. The amplitude becomes its highest that it can be, and that's a resonant amplitude for our problem and the resonant frequency for our problem. Okay, so that's a description of what we are after, and more than likely you're going to have experiments in mechanical and electrical that's going to duplicate this thing in a lab. Now, how about doing it mathematically? Let's set out to do this thing. Since the problem is about a bit lengthy, I'm going to try both of them at the same time, meaning I am going to just replace this 2 by W and solve the problem for the general case of W. And then at the end, you can always replace that W by whatever you want, and in particular, you replace it by 2, then you get this solution of this problem for 2. If dealing with a parameter is a bit too intimidating for you, then just go ahead and solve this thing from scratch. So let's get started. So after the first phase, what we are looking at is the following. Let me write it in U, language of U, so that textbook will be happy with me. U prime plus 490 U is equal to 10. You said let's put omega here and solve it in general so that we are answering part F and the previous portions all at the same time. U0 is 0 and U prime 0 is what we had, some peculiar number, 30 over 100. Okay, so this is the end of phase 1. So by now we are done with the modeling is done here. So this is phase 1. This is the end of phase 1. You remember we have 3 phases in these problems. So when it says formulate initial value problem, sometimes this whole thing is abbreviated to as IVP. That's what they mean. Give me the equations. Next, well, how do you handle this? This is complicated enough. Let's go make our life as simple as we can. Divide by 5 so that the problem and the numbers are a tad bit more friendly. How do you handle that? Well, write the characteristic equation of it, because you want to get for the homogeneous solution, you want to solve this thing without the cosine on the right hand side. So you get r is equal to minus 10 plus or minus 10 squared minus 4 times first and last numbers divided by twice the first number. So that's minus 10 plus or minus radical, and this thing turns out to be minus 292. divided by 2. And I can simplify that a bit by factoring a 4 out of that. Comes out of radical minus 10 plus or minus 2 radical 73, and minus becomes I divided by 2. So at the end of this long story, minus 5 plus or minus radical 73 times I. What does that mean? Well, it means UH, the homogeneous solution, is exponential of real part times sine and cosine of this frequency, cosine of radical 73t plus b sine of radical 73t. Okay, how do we get our A and B? At the very end of the problem, when we have our general solution, we come back and impose the initial condition and figure out what the A and B are going to be. But it's going to be a while before we get there. Now we go after the particular solution. Particular solution is a solution of the original equation. It's not the general solution, it's one particular solution. So 10u prime plus 98u is equal to 2 cosine of omega t. Once again, if this omega being here kind of unsettles you, replace it by the original, which was 2, and solve that problem first. But we are trying to keep this lecture short, so I'm trying to do both of them at the same time and hopefully save a little bit of time. But what do we do next? Okay, so again, big question. We are at the milepost. What is our next action? What method or idea do we use to move forward? So of course we are at the stage to use the method of undetermined coefficient. So here's a method of undetermined. The method of undetermined coefficient starts with the particular solution, which is the family of this. Given that this is not going to have a matching term against the homogeneous because of the lack of this exponential thing in it, just straightforward combination of sine and cosine of omega t is going to do it for us. Just be careful to use some other letters so things don't get mixed up. So for example, c cosine of omega t plus d sine of omega t. We are going to take this thing, plug it here, adjust c and d until this comes out. So that's going to be one more layer of this problem. So let's start with that. So I have u is equal to c cosine of omega t plus d sine of omega t. I differentiate easily. So minus omega c sine of omega t plus omega d cosine of omega t. Do this thing one more round. Differentiate again, and another omega comes out. Again, remember, if this was a 2 would have come out, and the next round a 2 squared would come out. But now is omega squared c cosine of omega t, and the derivative of cosine becomes minus, another omega comes out, d sine of omega t. What is the mixture formula? Mixture formula is to use 1 of this and 10 of that and 98 of this. Peculiar numbers, but that's what it is. So I'm going to take 1 of this, 10 of all of these things, 98 of all of that, equate to that. But when I'm combining this, I might as well collect my sines and cosines in different baskets. So let's put a basket here for all of my, say, cosines. Put another basket here for all of my sines. And this is supposed to reproduce the right hand side for me. So who's going to go in which basket? This cosine, it shows up here, shows up here, shows up here. So we have to take these coefficients, multiply with this weight factors, and add them up here. So 1 u double prime, so it's going to have 1 times this, which is minus omega squared c. 10 of this one, so I'm going to have 10 omega d. 98 of this one, so I'm going to have 98c. And then repeat, collect all the signs. So that's one of the things about this type of problems is there's a good deal of algebra involved. You have to be doing it very carefully and collect them and be on top of everything. It takes a bit to get used to it, and then it's layers after layers. So also test of stamina. So sine of omega t, what do I have? One of this thing, which is minus omega squared d, and then 10 of the middle one, which makes it minus 10 omega c, and 98 of the first one, 98d. Well, we have only cosine here, no sine over there, which tells us that it has to be 2 and this one has to be 0. Okay, the sine, there is no sine here. So what we have then, first equation, this is going to give us what? Let's clean this up a little bit because we are trying to find c and d, so I'm going to collect it. Minus omega squared plus 98c and 10 omega d. That parenthesis has to be equal to 2. This one I collect like this. I have minus 10 omega, c. That mistake there, c. How about d? Minus omega squared plus 98d. All of that has to match the sign on the other side. There's no sign on the other side, so this has to be matching 0. One more time. Remember, in your original problem, omega is a 2, so this would have read minus 20c plus, and then this is 4, and 98 makes it 94d equal to 0, and you're solving it. Now, omega is a parameter, so you will go about your business of solving just as before. What would you do here? Remember, we are trying to find c now, c and d. Omega is just a free parameter. So from this last equation, I go ahead, take this thing to the other side and divide by that. So I get, this is one way to write it. You can write it some other ways too. 10 omega d. Then I take this thing and put it in the first equation. So I'll end up having, so this c is replaced by that. I have this factor here and then again over there. So that factor becomes squared. So now it's the factor of d in it. And then there is another d, 10 omega d is equal to 2. So what do? We take this thing. Remember, we're trying to find c and d. Maybe it's a good place for you to pause and try to find c and d yourself so that you will come along with what we are doing. So pause this video for 2 minutes and find out for me what is c and what is d. So let me continue. What do? Here we take the d, take a common factor, and then in the parentheses I have minus w squared 98 squared over 10 omega, and then another 10 omega. All of this thing is equal to 2. When I square this thing, becomes d 10 omega it is best to leave these expressions as they are, as opposed to squaring them and opening them up. So your choice, but this is the cleaner format. It's like a completed square format. So it becomes 2 . So I have my D, and C is this expression times this fraction. When you multiply with this fraction, this numerator cancels this denominator, and that factor comes up. So very easily I see C is equal to 2 times minus omega squared plus 98. This cancels that, and I'll have minus omega squared plus 98 squared plus 10 omega squared. So you notice this 10 omega shows up everywhere, this one shows up everywhere, and this is this. So what do we have by now? What we have is our particular solution. Particular solution, remember, it was C cosine plus D sine. So what I might as well do to clean things up, factor this 2, which is common. This denominator is common. So I'm going to write the common factor 2. This denominator is for both of them, minus 98 squared plus 10 omega squared. This is a factor of 2. Then 10 omega cosine of omega t, and then this one is 2 times minus omega squared plus 98 sine of, I made a mistake. This is supposed to be C. It was C cosine plus D sine. I wrote it the other way, so let me go correct myself. Best thing to do is to start over again. Let me put the factor of 2 here. C cosine. So it's going to be minus omega squared plus 98. Notice that is the same as this cosine of omega t. D sine is a D. This factor here, D sine of omega t. So this is the particular solution. This is the response to the external stimulus, that is, how the system is going to oscillate. Interesting fact is that the frequency is out here. In the way we wrote it, you explicitly see that the frequency also shows up in the amplitude. So as you change the frequency, the amplitude is going to change. And that leads to the interesting problem we have, which is what is the most influential or the best frequency to use so that the amplitude of the response becomes maximum. Okay, before we do that, let's go ahead and finish up. So the problem was asking what? The problem was asking, okay, formulate the initial value problem. That was the easy thing. Find a position. That is, I want to find the solution. Once you have the solution, then you can graph it and then do all of these things. And so let's go ahead. What is the general solution? General solution is the homogeneous plus the particular. Homogeneous is what we had before, you remember? Homogeneous. The homogeneous solution and solution without the presence of the external force. That's simply this. Still two loose ends in it. What are A and B? But we left that for the end. So you write that. exponential of minus 5t times a cosine of the equal 73 square root t plus b sine of same. That's the general. And then the particular solution, which is just this whole thing. So we have to write it one more time. Minus omega squared plus 98 cosine of omega t plus 10 omega sine of omega t, and then you have the denominator minus omega squared plus 98 squared plus 10 omega squared. These are square of those two entries. Okay. Now or sometime in the future you can answer who's transient, who's steady state. This is however A and B turn out to be. We still have to figure out what A and B are going to be. This is what is referred to as the transient. It goes away, it washes away because of this exponential of minus 5t. It dies away. That is response to the initial kick to the system. If you had no external force, that's all there is, and it's going to die away. There's no exponential or anything that's going to make this thing die away. This is there forever. That's a steady state. Typically, you pay attention to steady state because this one is going to get washed away anyway, and A and B are dependent on your initial conditions. So to find u for our problem, what should we do? I want to find u. So again, let me see. I pause here for a second and ask you, what would you do and how would you do it? So we want to determine A and B before we go any further, because the text asks for graph the solution. But graphing the solution requires A and B. How do I get my A and B? So did you figure out how to do it? So we go back. Of course, that is the benefit of initial conditions. So to find A and B, what do? Use initial conditions. Okay, so initial conditions always come at the end when you have figured out what the general solution is. Then, okay, let's see. U0. Standard trick. Exponentials become 1, cosine becomes 1, sine becomes 0. So if this is quick, the only thing that's going to survive out of the first portion is just an A. From the second portion, sine falls out because sine of 0 is 0, cosine of 0 becomes 1. This lengthy expression is going to be there, so I'll have 2 times minus omega squared plus 98 over that stuff. So if in high school you did a lot of algebra, this is not going to be intimidating for you, but if your algebra problems were kind of on overly friendly side, this is going to look quite intimidating. So next thing is to figure out initial position. We kicked it from equilibrium position where u of 0 was 0. You remember? U of 0 so u of 0 was 0, u prime of 0 was some number. So from the initial equilibrium position, we just kick this thing down. So I use 0, 0. And next is u prime 0. Let me see if you can quickly take both derivative of this monster and insert t equal to 0 in that and figure out for me what's going to survive. Do you think you can put it together in 1 minute for me? What is u prime of 0? Take this whole thing, differentiate in your mind, with respect to t, replace t by 0, tell me what is left. Okay, let me encourage you to do that. Okay, 1 minute, maybe 2 minutes. So what do I think about this? Okay, I have to apply the product rule here. Derivative of this is going to be -5 times that. All that's going to survive out of this is the cosine term. It's going to be -5a. Then what? Then differentiate this term. In that case, sine becomes cosine, and that's the one that's going to survive. It's going to be b. But when I differentiate this thing, there's going to be radical 3 coming out of it. And this is just an exponential. So what's going to be surviving is b radical 73. So I'm writing a bit of a shortcut. You either learn the shortcut or just go through it by the long cut. How about here? When I want to differentiate, remember we are differentiating with respect to t. So cosine becomes sine. The sine of 0 is 0, so it falls out. Sine becomes cosine, and that cosine becomes 1. During that differentiation, an omega comes out. So omega times this factor times a 2, that's what's going to be, so there was a 2 there. And then there was a 10 omega there already. And another factor of omega comes out because of differentiation. And whatever was in the denominator is just some constant that's going to be also sitting there. Well, u prime of 0 will be equal to what? That was given to us is this peculiar number, 3 centimeters per second, or 3 over 100 meters per second. So from the first formula, of course, we figure out what a is going to be. So I take this into the other side, becomes -2 times minus omega squared plus 98 over this stuff. And b, well, I have to take 5a to the other side. Take this expression to the other side and divide by square root of 73. So here's a division by square root. This stuff is on the right hand side. 5a, 5 times this is going to come to the right hand side. So I'm going to have 5 of. There was a factor of -2. It's overall factor of -10. Omega squared plus 98. The denominator of this expression and that expressions are the same. So let me, while I'm doing this, let me also take a common denominator. Minus omega squared plus 98 squared. And this stuff also going to go to the right hand side. So it becomes -2 omega times 10 omega. The same common denominator as this. And that's going to be our b. So what is our final answer? Who's u? U. We are going to have this let me maybe write it in a way that actually fits in the line. It was exponential of -5t. Then this is our a, cosine of radical 73t. This b, all of it is going to come here. So and then the homogeneous steady state solution is going to be here as well. So we actually have to replace A and B by these two formulas, but the answer becomes so lengthy that trying to do that, it's going to spill into two lines. Okay, let me write this thing and then I'll come back and so here I have cosine and sine. Okay, I hope I haven't lost you guys to here. Some of you might be thinking, wouldn't this be a lot easier? Plug it on a computer and the computer is going to give you the answer and so on. Like this is not so pleasant because it looks like two lines of formulas. Well, you think so, but let's go ahead and check one of the very famous software that's available out there. Perhaps I shouldn't mention the name. When you go there and plug in this equation there as it is, and then you ask it for a solution, that is what it spits out. It's about a page and a half. So good luck reading that and trying to figure out what that is. So a computer is not always the answer to these type of problems. You notice that our solution is, well, 1.5 lines long, or maybe at most 2 lines long. And the computer solution was a page and a half. So compare a line and a half versus a page and a half. So even when you want to use a computer to do this kind of stuff, you still need to know your way around that particular software and figure out how to clean things up and so on. So if you're looking for an easy way out, sorry to say that there is no such thing. There's always a challenge in the way, and they might package something, put it in a computer and make it look like you made some progress, but in reality we are still facing that challenge. Okay, let's see. Back up there, see what was our plan. We formulate the initial value problem, we did. Find the position. Well, that's what we just did. After all that work, this is the position of the particle or the mass. Next, graph this. Well, I encourage you to learn how to use any of these graphic softwares, and we have been emphasizing Desmos. There are several of them, but any of them you still need to learn how to make good use of it. Typing in a formula that's 1 line long by itself is a skill you want to learn. Make sure you don't make mistakes and such. And here are some ways of doing that, like splitting into the pieces so that you can check them individually, make sure you have not made many mistakes and so on. So what does the graph look like? Here's the graph. That's what it looks like. You still have to play with your range and such to make sure the graph is zoomed in a correct way. We talked about steady state versus the transient. Transient you see at the beginning. We have kind of odd man out oscillation here. That's when the system is not settled yet, and then it settles, then you see. Okay, what else? Well, we did identify transient and steady state part. Find the amplitude of the steady state solution. Okay. We are building up to the last part of this problem, which is still a significant component to be done. Let me remind you, when you have a sine and cosine mixed into an expression, we've gone through that thing before. If you have a sine and cosine in an expression, Then the net amplitude. So let's go back to the following. If I have C cosine of omega t plus D sine of omega t, the net amplitude of this thing R, we had several exercises on this, is the hypotenuse formula, with C and D being the legs of a right triangle. So this is the amplitude. So the problem first asks, well, what is the amplitude of the response? And then for the finale, it asks, make the amplitude as large as possible. So what should I do? I have to square these two. These are my C and D. They have a common denominator. And square them, add them up, take square root. To make my writing a bit easier, I'll write R squared. R squared is just C squared plus D squared. So I wouldn't be putting a huge square root on top of my formulas. And that makes things a bit more manageable. So what is R squared going to be? R squared, I have a factor of 2 here, which is going to be 2 squared. There's this common denominator that's going to be as many squares that we have in it. We still are going to do one more square. So this whole thing is going to be squared. These two factors have to be squared and added up. So I have minus omega squared plus 98. Factor of cosine has to be squared. Factor of sine has to be squared. That's going to be the amplitude. Now we'll stare at this thing for a second and notice a very major simplification that if you don't notice, my life become a lot harder in the next stage. What is simplification that you see here? What should I do to clean it up? Notice anything? I should just take you 1 second so I don't put that picture up. Just stare at it for a second and tell me, how would you simplify? Well, it's very obvious. This is exactly that. That's the magic of this formula. So 2 squared stays there. That simplifies with one of these exponents there. So I have minus omega squared plus 98 squared plus 10 omega squared. So that's the square of the amplitude. If you take square root out of this, then you will have your amplitude. So if you wish, you want to find R, it becomes 2 over square root of that stuff minus omega squared plus 98 squared plus 10 omega squared. Okay, the finale of this whole problem is find omega so that R is maximized. So I have this formula, R is equal to this. How do I choose omega to make R to become maximum? That's a standard topic, high point of calculus 1. Think about that for a second. If you wanted to find the maximum of something, what would you do? Maximum of a function. You remember, take a derivative, set it equal to 0, and then there was a discussion to make sure you actually found the maximum. Here we can talk about this and make our life a bit easier. Of course, yes, you can go ahead and take a derivative of this, but pay attention to the following. If this wants to become maximum, then R squared will become maximum. R squared becoming maximum means this fraction becomes maximum. Since the numerator of it is a constant, it means its denominator should become a minimum. If the denominator is smallest possible, the fraction is the biggest possible, R squared is the biggest possible, R is the biggest possible. So here's a little bit easier than just differentiating that. Just differentiate this denominator and set that equal to 0. So now a shortcut to the step above. So to find that, take the derivative of the radicand, set it equal to 0. A lot easier than taking derivative of r itself. Well, what do you get? A factor of 2. Derivative of that is minus 2 omega. This raised to 1 less than exponent that you had, plus, how about derivative of that? 10 squared is 100. Derivative of omega squared is 2 omega. This becomes 200 omega. So now I go ahead and factor up minus 4 omega out of this. From here I have minus omega squared plus 98. From that one I factored omega. Factor 4 out of that leaves you with 50. So minus 4 omega times minus omega squared plus 48 equal to 0. 3 options, omega equal to 0. Then omega is equal to plus or minus square root of 48. Omega equal to 0, if you have frequency equal to 0, means nothing is moving on the right hand side. You have just a constant force. Well, that's not going to be interesting, and I'm not going to get into that either. Simply stated, that's not going to give you your maximum. Also, for frequency, we always go with a positive number. Negative frequency will result in the same thing. So omega becomes square root of 48, which if you simplify, I guess it's 4 radical 3. The nickname for this thing is omega maximum, meaning this is a frequency that's going to make this frequency makes amplitude of response to be largest possible. Okay, so that was the holy grail for today. We found this thing. It's almost 6.9, which is what we noticed in that demo that we had, that Desmos demo that we had. In fact, actually, I did make that Desmos to make sure my calculation, being as lengthy as it is hopefully doesn't have a mistake in it. So note, if I go to high frequency, you notice the amplitude dies out. When I come back to some middle range of frequency, the amplitude builds up, and you see it goes up, 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 8, 7. Well, exact answer is 6.9. Now, if you go past that, amplitude goes down again. So it looks like I got the right answer. And let's now, many of you are asking, is that going to be on the exam? It's a wrong question to ask. What you want to do is to, there will be several homework problems kind of similar to this. You can break the problem into pieces and answer it that way. As a shortcut, where does this thing come about? We can redo the entire problem with mass and damping constant, the spring constant, all of them replaced by mck, exact same procedure as before. It leads to the following. M omega max squared is equal to k over m minus c squared over 2m squared, which if you take a common denominator becomes 2mk minus c squared over 2m squared. So omega itself becomes the square root of 2mk minus c squared over, well, you can take the 2 out, and radical 2. That's the frequency that leads to highest response. Of course, this has to be positive for the whole thing to work. Otherwise, you can't have a imaginary frequency. So a requirement for this to happen is 2mk has to be larger than c squared. And if it is so, then of course it's going to be underdamped as well. But not every underdamped problem leads to resonance like this. So we have this formula to help us to get to the bottom of this thing in a few seconds. And I hope you go ahead and read about this thing in your text. There's a lot more detail there, but the algebra is not presented there. It's left to you to figure that out by yourself. Most engineering texts do have a section on this thing in much more detail, lots of interesting graphs and such, but we have other things to cover. Okay, thank you for coming along. I realize this was a lengthy and heavy lecture, but if you go back to the very beginning of the semester, you see that was our aim. We explained this type of resonance, and that's a major achievement by itself. What we are going to do from here on, we are going to jump to chapter 6, chapter on Laplace transform, learn how to do some of these problems in a much more abbreviated way, and learn about looking at the world from a different point of view, which is what the Laplace transform is all about. Okay, thank you again, and good luck, and God bless.